Welcome to this video on Kubernetes volumes, part of our Kubernetes storage series. In this tutorial, we'll explore one of the most fundamental concepts in Kubernetes, volumes. Volumes are essential for managing persistent storage in Kubernetes, allowing your applications to store and access data reliably. By the end of this video, you'll understand what volumes are, why they're needed, and how to use them effectively in your Kubernetes deployments. Let's get started. Before we dive into volumes, let's understand the storage challenges in Kubernetes. First, container file systems are ephemeral by default. This means any data written to a container's file system is lost when the pod restarts. Second, containers within the same pod cannot easily share data with each other without a shared storage mechanism. Third, stateful applications like databases need storage that persists beyond the pod's lifecycle to maintain data integrity. Finally, applications often need to access external storage systems like network file systems or cloud-based storage volumes. These problems highlight the critical need for a robust storage solution in Kubernetes. So, what exactly is a volume? A volume is essentially a directory that's accessible to all containers running in a pod. It has a defined lifecycle that's tied to the pod itself. Volumes solve the storage problems we just discussed in three key ways. First, volumes are mounted directly into the container's file system at a path you specify. Second, all containers within the same pod can access and share the same volume, enabling data sharing and collaboration. Third, volumes survive container restarts, ensuring your data persists even when individual containers crash or are recreated. This makes volumes a fundamental building block for any application that needs to work with data in Kubernetes. Let's break down how volumes actually work in Kubernetes. The process involves three simple steps. Step 1, you define the volume by specifying the volume type and its configuration in the pod specification. This tells Kubernetes what kind of storage you want to use. Step 2, you mount the volume by declaring where in the container's file system each volume should be mounted. Different containers can mount the same volume at different paths. Step 3, once mounted, containers can read from and write to the mounted path just like any other directory. Kubernetes handles all the complexity of setting up and managing the storage behind the scenes. This straightforward workflow makes it easy to add storage to your applications. Kubernetes volumes fall into two main categories. First, we have ephemeral volumes. These provide temporary storage that exists only during the pod's lifetime. When the pod is deleted, the ephemeral volume and all its data are also removed. Ephemeral volumes are perfect for cache data, temporary processing files, or any data that doesn't need to outlive the pod. Second, we have persistent volumes. These provide durable storage that survives pod deletion and recreation. Persistent volumes have a life cycle that's independent of any pod, making them ideal for databases, user-uploaded files, and any data that must be preserved. Understanding these two categories helps you choose the right storage solution for your specific use case. Kubernetes supports many volume types, but let's look at 4 of the most commonly used ones. First is emptyDir, which creates an empty directory when the pod starts. It's perfect for scratch space or sharing data between containers in the same pod. Second is hostPath, which mounts a file or directory from the host node's file system into the pod. This is useful for accessing node-level resources but should be used carefully. Third is configMap, which injects configuration data from configMap objects as files in the container. This is great for externalizing application configuration. Fourth is Secret, which works like configMap but is designed specifically for injecting sensitive data like passwords and tokens securely. Each volume type serves different purposes, and choosing the right one depends on your application's needs. Let's look at a basic volume configuration example. In the Volumes section, we define a volume named shared-data using the emptyDir type. The empty curly braces mean we're using the default settings. In the Containers section, we configure the volume mount. We specify that the app-container should mount the shared-data volume at the mount path/data. This means the container will see the volume contents as a directory at /data. Any data written to this path will be accessible to other containers in the pod that also mount this volume. This simple pattern forms the foundation of volume usage in Kubernetes. Now let's explore persistent volumes. Abbreviated as PVA, persistent volume is a cluster-level storage resource that's provisioned by cluster administrators. Unlike regular volumes that are defined within pod specifications, persistent volumes exist as independent cluster resources. They have three key characteristics. First, they are cluster-wide resources, meaning any pod in any namespace can potentially use them. Second, they represent admin-provisioned storage, typically backed by network storage systems or cloud storage services. Third, they exist beyond the pod lifecycle, so data persists even when pods are deleted and recreated. Persistent volumes provide a way to decouple storage management from application deployment, giving administrators control over storage provisioning while allowing developers to consume storage on demand. To use a persistent volume, pods don't reference it directly. Instead, they use a persistent volume claim. Abbreviated as PVCA, persistent volume claim is essentially a user's request for storage. Think of it like this. Persistent volumes are the supply of storage resources, and persistent volume claims are the demand. When you create a PVC, you specify your storage requirements like size and access mode. Kubernetes then tries to find a matching persistent volume and binds them together. This binding creates a one-to-one relationship between the claim and the volume. The PVC abstraction allows developers to request storage without needing to know the details of the underlying storage infrastructure. It's a clean separation of concerns between storage provisioning and storage consumption. Volumes support different access modes that define how they can be mounted and accessed. There are three primary access modes. First is read-write-once, abbreviated as RWO, which allows the volume to be mounted as read-write by a single node. Multiple pods on the same node can use it, but not pods on different nodes. This is the most common mode and is supported by most storage types. Second is read-write-many, abbreviated as RWX, which allows the volume to be mounted as read-write by multiple nodes simultaneously. This is useful for shared storage scenarios, but requires storage backends that support concurrent access. Third is read-only-many, abbreviated as ROX, which allows the volume to be mounted as read-only by multiple nodes. This is perfect for sharing static data or configuration across many pods. Choosing the right access mode depends on your application's architecture and the capabilities of your storage backend. Let's recap the key concepts we've covered. First, volumes provide storage that persists beyond container restarts, solving the ephemeral nature of container file systems. Second, ephemeral volumes exist only during the pod's lifetime and are perfect for temporary data. Third, persistent volumes and persistent volume claims work together to enable persistent storage that's independent of pod lifecycles. This is essential for stateful applications. Fourth, Kubernetes supports multiple volume types, each designed for different use cases and storage backends. From simple empty directories to complex distributed storage systems, there's a volume type for every scenario. With this foundation, you're now ready to implement storage solutions in your Kubernetes applications. Keep practicing and experimenting with different volume types to master Kubernetes storage. Thank you for watching, and happy learning.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.